talk about the flexible blades wind turbines. So, okay, please, Anand.
Thank you very much. I'm very glad to be here.
Sorry, can you share the full screen, please? Because here we see the slides, the two slides, in fact.
Don't worry, you look at the biggest slide, that's the one which is being discussed. So you see what's coming. It's not so bad. This is more presentative when you do PowerPoint, and I need some movies. I have a PDF, but you cannot play the
but
movies.
now we actually see the two small slides.
Now you see the bigger slide, right?
No,
okay.
Not yet. Yeah.
Okay, let me just display first movie, and I switch to the bigger slide if you want, but let me just start. So basically, I think you see my screen. That's what you see, and what you see is probably what I see. So this should be fine. Anyway, I'm rather glad to be here for this plenary lecture on the CIGOS 21 conference about emerging technologies and the applications for green infrastructure, and having a lecture which is, I think, quite appropriate, because there's a really big improvement that you can make regarding wind turbine technology, especially this question of the flexible blades that I'm trying to address in this. And so I both discuss ideas of having a giant installations or a system approach that is typical of wind turbine farms. So I'm Professor Adnan Ibrahimovic, a chair of computation mechanics at Technical University of Compiègne, which is part of Sorbonne University, and also the senior member of Institut Universitaire de France. This is a nice position we can focus on interdisciplinary research, just like this one. First, I have to say I regret I stopped sharing my video because my office at home is not so nice. It was much nicer to be here. The last time I was in Vietnam, I was welcomed by a number of my colleagues and friends. Among those friends, there are four of my former PhD students. As Phan Ba Hung, it is Ngo Van Minh. They are both professors at the University of Transportation in Hanoi. Then San Nam Do is a professor in Da Nang, and he's right now in France. And Thanh Hung. And I have another student, his name is Cong Nguyen, and maybe he'll go back to Vietnam, so I can have a basketball team of Vietnamese former students. Anyway, it would have been much better to be in Ha Long Bay than here, but what can you do? We'll keep going. We are professionals, and let's try to do the best for the conference. So there are really two main messages I wanted to say, rather than just giving you introduction, motivation, conclusion, perspectives. One is about how to choose the proper modeling, computation, and control when you allow for flexible wind turbines. And the second issue is how to get the best wind load estimates, because once you have an excellent model, you want to have the best possible loading. Otherwise, there's no point of having a very sophisticated model if your loading is very poorly defined. So there's complexity, of course, and you have a wind turbine in a farm, that means one after another. Then really what you measure in terms of wind speed is not actually what each and every of these installations is being exposed to, because there's actually all these phenomena that one installation in the way of the second one is perturbing the kind of wind that you can measure at the sort of out of the wind turbine farm. So the whole point here came from the challenge that was launched a couple of years ago by the European community, because if you know, Europe wants to position itself as a leader in this green technology, even though Europe is polluting much less than many other big countries, especially like your first neighbor, China. We are keen on reducing this technology. I guess the reason for that is that by introducing this, you also can have many technological innovations. So it's all about that. So in order to motivate really a very high level works, there was a challenge. It was launched in 2017, where they were giving 20 to 25 million if you're able to deliver wind turbine installation that can produce 10 megawatt a year. And as far as I know, nobody really managed to kind of meet this challenge. So if you really want to understand what this 10 megawatt a year means, you can take a very rough estimate. I mean, there's always sophisticated computation like the one we did in this paper of fluid structure interaction about what kind of power the particular wind turbine can produce. But very rough estimate says that out of all the wind power which is produced by the, let's say, wind of blowing at the steady speed you can basically recover 16 over 27 if you take into account that the density of the air in sort of is in dry atmosphere is roughly 1.23 kilogram per meter cube. You can say that roughly you can cover 2/3 of what is really entering as the wind. Wind is taking into account all this surface of the wind turbine, which is turning around, and multiplied by the velocity square. So the surface of the wind turbine which is going around is basically the length of the blade, L squared times pi divided by 1/2. This is the surface of the circuit. And basically you take 2/3 of that, and you can say if you really want to produce 10 megawatt, you will need the blades which are 100 meter long. So for the moment in Europe, we have something that can produce up to 50 megawatts. So it's really doubling the size of wind turbine blades. So there are many challenges to that. First of all, you have to kind of convince people that what is being used right now is not the best technology. And it's not that difficult. I would say people call this Microsoft of wind turbine technology. For those who are using different operating systems, know that Microsoft is a very old house. It started with DOS. So if you use this operating system, you have all kinds of challenges which are brought by the connection with the previous version of Microsoft. So basically, it is everywhere, but it's not really necessarily the best technology. It has been adapted to the Northern Europe. Basically, it's not surprising that the most development were done in Denmark and Northern Germany, where you have this wind speed which are steady. And so you basically, if you launch this, the kind of technology which was developed is here. Here we did simulation that you can have really like a very shallow sea, Northern Sea and Baltic Sea, and then wind turbine is turning around. What you can really typically see of the existing technology is the following. You can see that the blades are basically rigid, and the only thing which is moving is this what's so-called mat, is the column on which the blades are positioned. So if you now make blades to be much bigger, that is 100 meter long, that is bigger than the biggest airplane that we have, A380, of course, you can no longer pretend that these guys should be rigid, especially in order to have such a heavy long blade. You have to make it of light composite material, but it's another lecture. So basically, you have to take into account the flexibility of the blades. So that's definitely the first challenge. Overall, if you have flexible blades, it's much easier to start. Basically, starting the, let's say, rotation of the wind turbine with flexible blades is something which is easy. You can see the leaves of the tree are turning all the time, but what becomes really difficult if you have flexible blades is to control them. So basically, if you want to control, here's one inspiration coming from this dragonfly insect. We have lots of them in Japan and in Europe as well. They have these blades which are moving, or wings which are moving like blades in some kind of three-dimensional motion. So you can have a much better control. There's also idea of how to change the blades in some kind of other form to turn them into that. And of course, there's the idea of you have to make these blades to be smart enough in order to execute certain motion that is keeping a control guarantee. So this is again another lecture. I just wanted to signal that we're trying to work on that as well. Now, a second alternative is to not to use the one giant wind turbine, but to keep using the ones that we have, only put many of them together. This has been already used in many places. Here's one of these wind turbine farms in US, where you actually brought many of these guys together in middle of Oregon. Oregon is typically inland, and they have lots of type of land which has not been populated by people, so you can put lots of wind turbines. There's nobody there to complain. This particular farm can produce 845 megawatt, but there's probably hundreds of these guys that are sitting around. So the problem there, which is to estimate each of these wind turbine installation, what wind is actually is getting, especially if you're going to take a flexible blades, then you have to know what kind of wind it is getting. So this is sometimes, one wind turbine is a system, or actually multi-body system with flexible blades and so on. And then you have system of systems, means they're interacting with each other by channeling the fluid flow. And so this is a typical type of strategy that has to be really addressed in a very interdisciplinary type of manner, where the core skills that you need is mechanics, control, stochastics, and so on and so forth. Because stochastics, because you can never really estimate this with the full certainty. So if you really look into that, how we can model, I just wanted first to start with a kind of easy way of driving you into this modeling. Is you can start with the one-dimensional model. This is basically turning this into a so-called geometrically exact flexible beam. These are the works that we've done with one of my former PhD advisors from Berkeley, Bob Taylor, author of book Zinkage Taylor, and published in 2002 in Computer Methods, Plan Mechanics Engineering. Then we also did shells and also 3D solids. That's stuff that I'm going to present you a little bit more in detail. So you can see that inspiration for this comes from palm trees. If they are at the shore, and they have very strong winds. The way they adjust to the winds is basically they take the branches downwind. We call this in France un drapeau. It's like a flag. So there's no risk of a failure of the installation. So this is where we're eventually going to go to protect such a flexible blades from failing. So if I really want to comment on this, the key difficulty from modeling is coming if you take a geometrically exact 1D model. Basically, you can say that the beam in the initial configuration is this thick black line, and then the form configuration can have sizable displacement and rotation. And so typically what we're describing is the motion of the cross-section that we assume to be non-deformable. So this motion is taken by the large rotation. So large rotation, three-dimensional rotation are the main difficulty in representing this type of thing. And we can do that in so-called geometrically exact way. In other words, we actually take orthogonal tensor, which is constructed by so-called quaternions. This is 4-parameter representation of orthogonal tensor, the only one which is unique and use computation. You can also, for easy understanding, construct the large rotation by rotation vector theta, but that one is not unique. If you go with a certain limit of 180 degrees, you actually difficulties understanding which component of this rotation vector you should take. But let's say for the moderate rotation, you can also get this one. And again, orthogonal tensor could be constructed to this rotational vector by exponential mapping. This is done here. So basically, if you really want to control, you can see that this geometrically exact beam model is able to, for the, let's say, free vibration, to conserve energy. In other words, this is kinetic energy. The advantage of geometrically exact formulation is that the inertial term is very simple. It's just quadratic form in velocities in terms of displacement and rotations. And the complicated part becomes, of course, internal force, because now heavily non-linear, depends on this large rotation and so on and so forth. And you can show easily if you just set in motion by initial displacement or velocity, your Hamiltonian, which you see the total energy, that is the strain energy plus the kinetic energy, will remain constant. So if you really want to be able to control, you have to keep, for the case where the external loading stops, you have to keep your energy constant. And you'll see this is the kind of philosophy that you're trying to adhere to. By the way, people already study this, and this is a collaboration we started developing how to control the large motion of what I call 0D model. This is a very simplified model of a drone, where drone is represented by a potential energy, M being the mass of the drone, G is the gravity of acceleration, and Z is the position of the drone with respect to the center of the Earth. You can see the potential energy of the drone is simply the drone, like each of us, by its own weight, is drawn to the Earth, and basically that's the case of the drone. And then kinetic energy, you take into account both displacement, this is linear momentum, and the angular momentum rotation. And again, this rotation brings in this large rotation, so you need quaternions and stuff like that. So the idea is how to control is basically to split the energies into the kind of strain energy and the energy that you supply through the loading, and basically you can stabilize by the keeping this difference under control at any time. And that's really for 0D model. That's what you're trying to apply now for 1D, 2D, and so on and so forth. Only you don't have a single point, but you have like a distribution in 1D or 2D and so on. So you could see that energy conservation is something very important, not only for the control, but also for keeping the computation stable. In other words, here's one very famous benchmark proposed by Olivier Boschot, who at a certain point was in US, and then he switched a little bit to China. I think he was in Shanghai and then in Hong Kong. Nowadays it's probably in US again because of this COVID situation. So the idea, he suggested this sort of a multi-body system with these two links are almost rigid, and this one is flexible with a heavy mass sitting in the middle. Then you hit this mass with some kind of triangular pulse that goes until 0.25 seconds, and you just let it swing. So this is a Boschot swing. So it starts swinging to the left, just like you are a child, you're swinging on these swingers. And then at a certain point, when you, this is precisely around 0.64 seconds, if this link starts going up, the other one has to turn the motion in the opposite direction. And that's precisely the moment when the axial pulse is introduced in this flexible link. And this has been all modeled by beams, and you know beams ever being very slender, they have a much bigger, what you call it, stiffness with respect to the axial deformation as opposed to the bending deformation. So initial phase of the swinging is dominated by the bending deformation. In other words, you have very kind of a low frequency. And then basically, once you start turning the direction of this other part, you introduce high frequency because of the axial deformation. So you can see at that moment that energy conserving is really start having a decay, and we can capture there with a scheme that I'm going to comment. And basically, if you take an energy conserving scheme and look into axial deformation, and axial force in this flexible link, you can see that following this event, when the axial impulse is introduced in the link, you have basically stresses which are completely useless, because typically here we had only 8 elements. You cannot really cover all this. You cannot represent the high frequencies correctly. So the only thing you can do is remove them. So the so-called energy decaying scheme, I'm going to comment how you actually do that. So this is the kind of thing you can see the benefits. This is energy conserving scheme. Let me just show you these movies very quickly. That's why I put this. In this energy conserving, you can see that vibration kept going. You actually conserve energy throughout this, but you can see that it's not really smooth. Whereas here, this is energy decaying. You turn around, you have a very smooth motion, and it carries on over and over again, which is not the case of the other guy that conserve it. So let me go to 3D modeling. You should do the same thing, only we allow for the case that the wind turbine blade can have a very optimized type of form, which is not easy to represent by a single beam model. So we represented with 3D solids, where actually here is the initial configuration, is the form configuration. And the key point is what is the strain measure to be introduced to monitor this type of deformation. In particular, we choose so-called biot strain, which is not usual choice of your green Lagrange and stuff like that. It is following from the polar decomposition, where you send the deformation gradient into the rotation. This is the same rotation like the one that you use for beams. And the stretch. Stretch is the one strain measure, which is kind of intrinsic. It's simply how much you stretch from the initial to deformed configuration. If it's becoming 2 times as big, you say stretch is equal to 2. And then subtracting identity tensor, you get something called the biot strain. So with these type of things, you can then build your total potential strain energy. First of all, you have like a membrane. First of all, here's like a kinematic part. So there's a total energy, sorry about that. And then you have a strain energy. And then there's an additional part, which is taken into account the skew symmetric part of the strain measure to be under control. So we have to select after that the discrete approximation that has been done by using standard finite elements plus incompatible modes. So the standard finite elements, we are using the 8-mode solid element with this linear interpolation in 3 directions. And then incompatible modes, you're just enriching displacement with the quadratic shape functions. So this way you can actually have a very good representation of the bending moments. So here's this some of these examples. One point is, for this extra rotation degrees of freedom, mass is not really represented. So if you have a mass with a 0 term, it could be really dangerous, because 0 term in mass, it means infinite frequencies. The presence of the infinite frequencies computationally could definitely be very dangerous. So that is why in computation we're using regularization with very small value here to keep mass, let's say, fully rank sufficient. And you can see that there's certain advantages. You don't change the response too much, but regularizing the mass, keeping it fully sufficient, you can carry on computation for long term, which is precisely the goal when you're studying the risk of fatigue and things of this kind. Whereas if you have a 0 mass, if you don't do regularization, at a certain point the computation becomes too fragile and stops. So basically, the reason how we build these time integration schemes, you're probably familiar with Newmark scheme, which is kind of an average acceleration. Here we take something which is called a midpoint scheme. We actually introduce the difference between 2 displacements as a let's say, the average of the velocity in the middle. And then we switch in computing the strains, not to this type of approximation, but to the approximation. That means you don't take a axial force or whatever, the moment to be computed at n plus 1/2. Remember, these are nonlinear measures, but we take value at n and value n plus 1 and divide it by 2. So these two are not the same. This is so-called algorithmic constraint equation. They're precisely designed so the energy gets conserved. In other words, if you suppress external loading by using this type of algorithmic computation for your internal forces in a 3D solid, you're going to make sure that energy in n and energy n plus 1 will be the same. And that actually would keep stability of computation for very long term. Then we saw also that if you have an event that trigger high frequencies, then it's kind of desirable to suppress this participation of high frequency. So I just focus on this constitutive rotation. So if you have a high frequency, the difference between value at n and value n plus 1 could be quite high. So typically take it out with this coefficient and you take it out from your computation. Whereas if you have low frequency, given time step, the difference between the strain at n and strain n plus 1 will be very small. So basically, you're not going to modify the low frequencies. And you can see that in this computation. This is again Boscho's string, but computed from 3D solid elements. And you can see that basically we have the same desirable effects, that decaying of the energy starts here with this scheme. and that basically the axial force is not computed well with conservation scheme, whereas here it just comes down and you keep it constant over the time for the energy decay scheme. So we use this to kind of model existing wind turbines. Here's one of these 5 megawatt installation. We are actually monitoring the points that are at the far end of the blade and in the middle here. And you can see that the interest of using our solid elements with the enhanced bending deformation is actually there, especially when you have outer plane, which is dominated by bonding. Then it's also interesting to use our energy conserving scheme, because after a while, Newmark scheme is not able to keep the energy conservation, just simply explodes. You can see here that the instability starts very early for the computing velocity, whereas our energy conserving scheme goes on and on. Now, if you're looking into acceleration, even energy conserving scheme is not good enough. Of course, Newmark explodes immediately, but basically what you need is something like this decaying scheme, because then the acceleration, your stresses as computed as something meaningful over a long period of time, even if your finite element mesh is not excessively refined, that you have very, very tiny elements to be able to represent the high frequency modes. So you can do that with a reasonable mesh, but do this approximation in a better way. And you can see we were playing what form to give to these blades. You can keep them straight, you can kind of curve them in the direction of the wind, in which case, of course, you kind of reduce the tangential force to the blade, or you increase it, depends on what you're doing. And we're also playing how to curve it in the opposite direction. In other words, when the wind is hitting into the back of the wind turbine, given that these are very large, let's say, cantilever beams, these are 100 meters long, you can have very sizable bending effects. And you can see if they're straight, you have lots of bending here, so there's risk of failure. But if you just curve it a little bit, you can see that the membrane forces start dominating, and then you can certainly risk much less of breaking this thing. So this is all about modeling of a single installation. Let me just go quickly through this wind load estimates. Basically, if you put the wind turbine farm, this is actually represented here. The next installation is already suffering what first installation is doing. In other words, you saw the draft estimate was that the wind turbine will take 2/3 of the wind when it goes there to deliver the energy. So the second one will not going to have the full, but it will have just 1/3 of what is left. And so you have to estimate when they're in the farm how much really every installation is experiencing in terms of the wind load. And we have 3 methods that we discussed. There's a panel method, very quick computation. There's a real fluid structure interaction, Navier-Stokes and geometric exact structures. And then there's also measuring by Bayesian inference. So if you look into the panel method, we started with a very simple hypothesis. First, that fluid is incompressible. In other words, that the gradient dot velocity, the divergence of V is equal to 0. And then the flow is also irrotational. So if it's irrotational, we can have representing with the vorticity. This is one way out there, or we can do it with the strength of let's say, vortex, which is here called gamma. And this strength now could be represented by using the computation. In other words, we take the interface between solid and fluid, we divide it into the panels, and then we say that the vorticity is computed as an integral over this, let's say, the edge of this particular panel using this Biot-Savart law. And then basically we can take the wind turbine and divide it in panels, typically, and you imply that fluid structure interaction would mean that the fluid velocity and solid velocity at certain direction of the normal have to be the same. So this solid velocity can be computed by the steady rotation of the blade. So the rotation being exposed by omega, and r is a radius from the point around which it is rotating. And then you set this equation, you express your velocity interaction to be done in terms of this strength of the vortex. Plus you add on that, you make superposition, the velocity before you enter the farm. And then from then on, you can develop the set of the equations in terms of these velocity strengths for each and every of these panels. Of course, this set has to be considered to be unique, and this is done by using the Kuta condition that actually vorticity on one part and the other part will actually join together and become the same. After that, when you computed your velocities by using this, you can use the Bernoulli principle and say that the energy along a certain streamline remains the same, and you can obtain all the information that you need for your computation. So this is actually fluid computation, which is kind of boundary element, because the only thing that you're presenting are these fluid structure interface and nothing else. All the rest is solved analytically. And so this is adapted by using it into the solid model of your wind turbine blade, where exposed facet of a solid element that is exposed to fluid is used for this type of computation. So after that, you had to do a fluid structure interaction. If you want to do implicit computation for the given position of the solid, you carry out the computation of fluid, then you move the solid under this fluid, then you do again computation of the solid and so on and so forth. So it goes step after that. You can do it iteratively in order to match perfectly the solid and fluid interface. We have done that by coupling this finite element computer code, Bob Taylor from Berkeley, and MATLAB. MATLAB is doing panel method, and Flip is doing the geometric exact computation of the structure. And basically, here we suggested that this can really give some very interesting results, especially if you have this kind of the total force applied to the particular wind turbine, which serves to design. We compare that with the kind of more simplified methods and so on and so forth. And you can see that basically this computation could be quite interesting as we go along. There's interest of really doing implicit fluid structure interaction. In other words, that you really try to converge, because then you improve your results as opposed to not iterative method. I'll just skip this very quick. The second method, we said the panel method is very quick, but it doesn't really give you fully all these turbulence type of stories. So if you really want to do turbulence story, then you have to do full Navier-Stokes plus geometric exact structure. That's what you've done already. This is your typical interaction between solids, which is geometrically nonlinear. So there's only internal force to be here nonlinear. And this is your Navier-Stokes equation, where you can see the motion of the mesh given here. So you have all these unknowns, which are displacement of the solid, the velocity of the solid, the velocity of the fluid, and the motion of the mesh. And then you have to actually impose the connection between solid and fluid. And in order to make sure, again, this is done with the sequential resolution by splitting the codes. First you hit solid, then you hit fluid. Solid is done by FEEP, fluid is done by open form computation. And if you want to be stable, there's certain type of procedure you have to do. In other words, you have to move solid first and then fluid. This is one of these benchmarks that we use, driven lid cavity flow. In other words, you just put the shear pulse, which is varying in time, and normally the edge of this box is rigid, but here you have very, very flexible membrane. So you can see what it does. These are kind of rotisty lines. There's a membrane which is deforming very heavily, and this is the way how we control pressure. You typically have to put the pressure outlet in one point, and again, membrane is deforming very heavily. Normally, we are not only interested in these benchmark problems, but it's difficult, and I'm sure that we're interested now in modeling something in turbine. Here, we took a very simple model 2D, and you can see now that this is the illustration of the geometric exact model vibration and the streamlines, and you can see that it becomes much harder to control. Now, what we really plan to do is turn these blades into the multi-body system. And when you reach this ultimate type of loading, you simply release the joint and you let these blades flow like a flag. So you avoid the risk of breaking the installation, which typically is likely to be very costly if you have very strong winds. So the final way of how you estimate the wind load is simply by measurement. In other words, you can measure the let's say the deformation and wind speeds at certain points of a wind turbine, typically strategic points either on the support or on the blades. And then you start to reconstruct the loading in a very quick way by Bayesian inference. How does it work? Well, basically, this is your typical approach by Kalman filter. You can integrate the tower kinematic equation from acceleration. Then you correct with the tower strain gauge curvature reading. Then you integrate blade kinematic equation from blade and tower acceleration. Then again, correct with blade strain gauge and so on and so forth. This is your, let's say, the Kalman gain matrix that is typically set once for all, and then basically update goes very quickly, and it's almost like a linear computation. Now, when you have this computation, you have to know in terms of control when to interfere. So you have to leave yourself a certain period of time before you can actually correct the motion. So this really is like a, what you call it, incremental type of approach, where you have to have a sophisticated equipment which can actually control motion, and especially signal when you have to put it in undrapper, what they say, as a flag that not to break the installation. So these are kind of two main messages that I really wanted to deliver for this lecture, and I think I'm in time, given that we started 2 or 3 minutes later. First is that when you have one possibility to have a giant wind turbine with 100-meter blade, you have to do very sophisticated modeling and very sophisticated computation, and of course, hoping that you have the best control to keep your installation safe. The second point is if you turn now to the wind turbine farms, you have many of them. The main challenge becomes really how efficient that is, given that you have a lot of interference, the wakes, what do you call it, between one installation and another. So how to estimate the wind load to keep the whole installation very efficient is certainly a very big challenge. We have focused here about particular installation about energy. There's also
Hello, Moto. Bonjour. D'accord, j'attends. Est-ce que vous êtes ici à Roberval, à la résidence universitaire? D'accord, j'attends. J'attends. D'accord, à tout à l'heure.